Well, welcome back. This is going to be a interesting video for you. We've just learned to draw influence lines using the tabular and equation methods. So now we're going to learn a shortcut. This is called qualitative methods. When we're done, you'll probably ask, why do we bother with the tabular and the function methods? But as you say, you kind of have to learn to crawl before we run. So this is going to be called the Mueller-Breslau method. Let me share my screen with you, and we will begin. So this is qualitative influence line. So what this technique will do, it'll give you the ability, after a little practice, of drawing an influence line or the shape of an influence line extremely quickly, like without calculation. And then you'll have to go back and with a little practice, you can find out the values of the influence line. So actually now drawing influence lines will become rather straightforward. And we have this skill based upon Mueller-Breslau. You might remember Heinrich Mueller-Breslau. He came up with this method for rapidly constructing influence lines. There he is again. And you might remember when he was born, he also helped come up with with a conjugate beam method with Dr. Moore. And he was a professor of civil engineering in Hanover. So thank you, Dr. Mueller-Breslau. So what is his principal state? It sounds kind of simple when you first say it. Application is a little tricky, but he says the influence line for whatever you're looking for, whatever function, reaction, shear, moment, is to the same scale as the deflected shape of the beam acted on by the function. Those easy words to read. What does that mean? Well, it means if you want shear influence line, you take the beam's shear capacity away, apply shear force, and what shape would that beam move to? So let's see how this would work. So let's consider a simple supported beam. Here's one, A to B. And what we want to do is we want to find the reaction of the influence line for the reaction at A. So what I'm going to do is I'm going to go to A, and I'm going to remove its ability to withstand reaction. It's gone. And now I'm going to apply that reaction to it. Now looking at that situation, how would that structure move? Well, if I'm pushing up, if I'm assuming my reaction is up, you can see the left edge of the beam would move up and the beam would then pivot, as you can see, like this. So that shape of the deflected beam under this interesting Mueller-Breslau hypothesis then becomes the shape of the influence line. And then we know if we go back and assume our unit load is at A, then the value of the influence line at A is 1. And I could find the value at any other point along the beam using similar triangles if I knew the distances. Pretty cool. All right, let's see what happens now. Let's do the same problem, simple supported beam, except let's look at shear, in this case at the midpoint. I've never seen one of these before, but this is my rendition of a shearless connector. So you can see it still has the ability to withstand movement horizontally and also to withstand moments, but you see it can't handle shears because of these rollers. So this is the so-called shearless connector. So now let's apply positive shear on the left side and positive shear on the right side. And you can see the left side would then move down. And the right side on positive shear, that edge would move up and rotate like this. And if I transfer this down, then that is the shape of my influence line. Now, what are the actual values? Well, one thing we know is that the change as you go from the left side to the right side has to equal 1. Remember, our unit load for moving loads is 1. So I know that change is 1. So if I know these dimensions here, say D1, T2, then again, similar triangle will help me find these values. Pretty cool. What about moment? Well, moment's probably the easiest one to visualize. You would go to the point you want, let's say C, and I would take the ability of the beam to handle moment away. Well, that's just a hinge. And then if I apply positive moment to the left side, positive moment to the right side, I'm looking at that point, which way would it want to move? Would it move up or down? Well, it's going to want to move up. So the deflected shape of this new beam would look something like this. And then there's the shape of my influence line for the moment at C. Now you're probably cussing me right now saying, why do we go to all that trouble to do tabular and write all those equations when I can just draw it simply? And again, I'll just say that, you have to really understand what's going on before you can learn the shortcuts. So what about the reaction at B? So here's again a structure. I'll go to B. I'll remove the B support and apply the B reaction. How is this structure going to move? Well, point B will move up, and the beam would rotate into this position. And there is your influence line for the reaction at B. In this case, we know when the unit load is over B, By will be 1. So then I could find any value I wanted based upon the distances along the graph, again by similar triangles. What about the influence line for the reaction at A for a structure like this? Well, that's a cantilever connection at A. So again, I'm going to put my, in this case, reactionless or shearless connector there and apply that reaction. So how will the structure move? Well, the whole thing's just going to move up. So therefore, my reaction, or my influence line for the reaction at A, is just going to be constant. And again, with a quick little check with my statics equations, I know that value will be 1. We've actually done that problem before. You might remember that one. Let's talk about a reaction at B when maybe B is internal. Well, the process is the same. I'm still going to remove my B support, apply By, and how will B move? Up or down? It's going to move up. So therefore, my beam will rotate into this position, and I'll have my influence line looking something like this. And what value do I know? Well, I know when my influence line is right over B, By is 1. So that's the one value I'll know for sure. And again, if I know my dimensions of my beam, I can find the value of the influence line anywhere else along the structure, including the maximum value out here at the end. Let's look at the influence line for the shear at C, where a beam looks like this. Okay, now they're getting a little more complicated, but surprisingly, you'll find that the process is much the same. So again, I'll go to C, and I'll put my shearless connector, apply positive shear on the left side, positive shear on the right side. Now, how's this going to move? Well, you can see I have a lot of different points that I need to denote, and I'll go ahead and do that. So what's going to happen here on the left edge? Well, that point, is it going to move up or down? Well, it's going to move up. This section has to move up, and this section has to move down. And like a seesaw, it will seesaw over B. Because we have a hinge, it'll connect back to A. So that's how I get the shape of my influence line. Now, if I had to do this with equations or the tabular method, I would end up with one relationship here, a second relationship here, and a third relationship here. It would take me the better part of 5-10 minutes to come up with those equations to make this plot, whereas using Mueller-Breslau, I can almost sketch it by looking at it, by inspection. Again, I'll know that that point, the total change here has to be equal to 1. And if I know my dimensions through the slope and similar triangles, I can find all the other important values. All right, let's look at this one. What about the moment at C? Same beam, but now I want the moment at C. So in this case, There's my momentless support, hinge, positive moment, positive moment. Now, is point C going to move up or down? Well, it's going to move up. And because it's going to move up, then what's going to happen? Well, this piece will have to go up, hinge, seesaw over B, hinge, connect back to A. And very quickly, I have the shape of my influence line. Now, unlike shear with moment, we don't have a clever little connector here. So what I'll have to do is I'll have to say, I want to find the value here. Okay, and what that means is I'm going to go back to my original structure. Let me remove these marks. So if I want the value here, I'm going to have to go back to my original structure and assume that's where my unit load is, my value of 1. And then I want to find the moment at C due to that. And when I find the moment at C due to that load, that will give me this value. And once I have that value, again, I can use similar triangles to find other values. What about the influence line for the moment at B in this structure? Well, again, I'm going to apply my momentless connector, which is a hinge. There's my positive moment on both sides. Now, is B going to move up or is B going to move down? Well, it's going to move up. So when you do that, connected at A, I'll go up, I'll hinge, and then I'll seesaw over point C. And there's my influence line. And again, as I mentioned in the previous problem, if I want, say, this value, then I'm going to come back to my original problem and assume my unit load is at that point. And then I'm looking for the moment at B, which is over here, due to that load. Once I get that value, this will give me this value of my influence line. Again, similar triangles will give me the positive value. So let's look at the influence line for the shear at V. Okay, hopefully we're getting a little more comfortable with this. So I go to B, I put my shearless connector in, I apply positive shear on both sides. And what do I get? Well, the left side is going to go down, so I'll get a hinge here. The right side is going to go up and then seesaw over C. So I'll get a shape that looks something like this. Now it is shear, so I know that this total change here will be equal to 1. My change in shear should be equal to 1. All right, so how about the vertical reaction at D and the shear at C? So this is the first time we actually have numbers. So we'll actually be able to put values on our graph. So let's start with the reaction at D. So just like before, I'm going to remove the D support, apply dy. Is that point going to move up or down? Well, think about it for a second. I think you can see by the way, assuming that it goes up, that I'm going to know that point's going to move up. Everything else is attached, so it will hinge here. And my influence line will look pretty simple. It'll look like that. And of course, over dy, the value of dy is 1. And there's my influence line. What about the shear at E? Well, I'll use my neat little shearless connector and apply positive shear left, positive shear right. And then what am I going to get? Well, this side's going to go down, this side's going to go up. So I'll rotate down, seesaw over B, hinge at C, back to D. And I'll get a shape that looks something like this. That's pretty cool. We were able to do it so quickly. So again, I would have to have written one set of equations here, a second here, and then a third here, whereas I was able just to sketch this almost by inspection. Now we do have values here, so we can now look at numbers. So I know that is a change of 1. then what are we going to do? Well, this and this are equal, 10. That means the heights have to be equal. So that means those values have to be 1/2. 1/2 plus 1/2 is 1. Now, how do I find this guy? Well, I know this triangle, the 1/2 to 10, should be equal to this triangle. I don't know what it is to 15. So when I solve for that h, you can see I get 0.75. So now I know this value here is going to be minus, because it's negative, and the value of, 0.75. So now I have quickly been able to draw my influence line. In the previous problems where we have a live concentrated load and live and dead uniform loads, I can then use the portions of this influence line to solve those problems. So if you look in the notes, I think this will be problem 6B1. You can look at this problem and see how I've solved it, but do notice that we have a concentrated load, a uniform live load, and then a dead load. So again, with the uniform load, remember we're going to start and stop that load over the areas where it'll create the maximum positive moment. That's the positive areas of the influence line. Okay, so now you know how to use Mueller-Breslau, and you can continue to work these influence line problems. So I'll stop sharing the screen and come back to you and tell you again, if you have any questions or any problems, just email me or call me. There'll be homework for this. I think these will be mastering engineering, so keep an eye on that. The previous homework was on paper, and you'd have to upload your results. So until next time, be safe and see you later.